Buddy, this is Dan Wire. I am Vice President of the Maumee Watershed Alliance, and I'll be moderating the sessions this morning. Thank you all very much for taking some time out of your morning to not only share, but for those that are watching, listening, and learning about water quality and what we're doing within the Western Lake Erie Basin. So just to sort of set the parameters here, Western Lake Erie Basin, the first two feeder rivers, St. Joseph and St. Mary's, come right through downtown Fort Wayne, kind of the headwaters. The Maumee Watershed Alliance, not trying to bite off more than we can chew. We're looking at basically the upper Maumee watershed, which includes those watersheds of the St. Joseph and St. Mary's and the upper Maumee until about Defiance. So we also want to show our appreciation for the Allen County, Indiana Soil and Water Conservation District. That's where we're housed right here in their conference room. The Nature Conservancy, the USDA, NRCS for a lot of technical and financial support. Then of course the Maumee Watershed Alliance. We want to thank everybody that's taken some time to join us. We will be recording this. It will be on the website. We may have an opportunity to sort of break out these little sections so somebody wouldn't have to watch all 3 hours and come back to a particular section of it. But this morning we're doing it in 3 parts. From 9 to 10, we're going to talk about the science behind water quality challenges. From 10 to 11, we're going to talk a little bit about the economic impacts. And then the final hour from 11 to 12, we're going to address some of the successes. And all of these are going to have a balance between rural and urban because we are all in this thing together. Starting off this morning is going to be Mark Williams sharing with us first, and then Chris Winslow. But to start this off, I'd like to just share a little perspective from the urban side. And it's been about a decade now, but I didn't know anything about anything outside the city of Fort Wayne. And I got associated with the Soil and Water Conservation District. And boy, have I learned a lot. And maybe it's the old phrase, I know enough to be dangerous. But what I do know about Fort Wayne, and we're one of 700 communities around the nation that have combined sewer overflows. So my involvement in water quality first was dealing with the sewer systems. And, we've got a major tunnel project that's going in right now. That's going to be a very expensive project. But even the old combined sewer system, it still works, it still functions. And as a matter of fact, on a day like today, and I trust everybody has got just a beautiful, clear day today, our capacity is just fine, even in the old systems. So it became pretty apparent that maybe, if I say this simplistically, we really don't have a sewer problem. What we have is a stormwater problem. And Mark Williams, in kind of testing out his slide, I love his first slide that's going to tie into this. So to get things started, farming is the dominant use of land throughout the Western Lake Erie Basin. And it's an interesting business because the farmer is going to do all they can to ensure a profitable harvest and be a good steward of the land. But the wild card in all of that is the weather. Nutrients, moisture, sunshine, they're likely the most important elements of this 3-legged stool. However, too much and too little of any of these is going to spell trouble for the farmer. And 2 of the 3 legs of this stool really are, how do the farmers control the weather, sunshine, and moisture? So Mark Williams is here with us to start off. He's with the USDA Ag Research Service, and he's focused on National Soil Erosion Lab. And Mark, if you want, when you get started, feel free to share a little bit more of your experience as appropriate. And to set the stage, I'd like to remind everybody that science is always evolving. To some, that's a blessing, and to some, that's a curse. And I hope that what Mark is going to share this morning is going to be a blessing, and that is going to provide that informational tool to better understand the emerging trends of weather. And this information will not only be helpful to agriculture, but also watershed management, water quality efforts throughout the Western Lake Erie Basin. So Mark, take it away, and thank you.
Yeah, let me share my screen here. I'll get the presentation pulled up so we can get that up and running. So my name is Mark Williams. I'm with the National Soil Erosion Research Lab.
We got a
in
Dan
West
conference at 9.
What?
Dan
West
White.
Lafayette. And so today, my title of my presentation is "When It Rains, It Pours." A few years ago, Kevin King from ARS in Ohio, we had this. We were attending a lot of meetings, and we were hearing folks say over and over again about rainfall and rainfall patterns and rainfall intensity. And that's what kind of motivated us to do a little deeper dig into the patterns of rainfall in the Western Lake Erie Basin. So today I'm going to focus really on three questions. The first being, has rainfall amount changed over the past 40 years? What about rainfall intensity? And how have these changes occurred throughout the year or seasonally? And at the very end, we'll touch a little bit on tributary discharge and also phosphorus loading. But the reality is, this presentation only covers a small kind of high level overview of the paper that we wrote. The citations there below, I also have it again at the end of the presentation. And if you'd like a copy of it, feel free to reach out to me and I can send it to you. So again, when we were starting to think about this, we were asking ourselves the question, are these big regional and national scale assessments of climate useful? This is an example of one for the entire United States. And the answer to that question is yes, they are useful. But if you look at that map, you kind of see that pretty much the tri-state area of Indiana, Ohio, and Michigan are largely the same color. So the level of detail isn't that great for more local scale issues. So how do weather patterns influence, agriculture at a local watershed level? That's not really apparent from these kind of maps. And why do we care about the climate? And that's because rainfall and soil moisture, kind of like Dan said at the beginning, control discharge. This is the only field level data I'll be showing today. But this is from 3 of our edge of field sites, showing tile discharge as a function of the soil moisture deficit and rainfall amount. So on this kind of graph, you can think about the far left being very dry. And as you move to the right, it increasingly becomes wetter to the point where rainfall is greater than the amount of water the soil can hold. And you see this kind of hockey stick shape to the graph where there's really no flow when it's dry. And then as you approach where the soil is becoming saturated and when rainfall exceeds that, then you get a big uptick in the amount of flow you get. And each of the colored dots there represent a different site. So you can see that the patterns are fairly consistent across these 3 sites that we had. So have changes in rainfall been uniform across the basin over the last 40 years? To answer that question, we got on the National Weather Service and we downloaded daily data from 1975 to 2017 from 23 rain gauges you can see on the map on the left there, and 12 river monitoring locations from the USGS. And our kind of criteria were we wanted to cover the entire basin, of course, and we also wanted the time series to be pretty complete. So each of these monitoring points on this map have greater than 90% complete time series, and the average was 98%. The reason we started at 1975, it kind of corresponded to when Heidelberg started monitoring, so that was also a good time to start. And also, once you get earlier than the early 1970s and moving into the 60s, a lot of these points don't have data. So we limit the number of data points we had if we went too much earlier than 1975. And we cut it off in 2017 because we started this analysis probably in December of 2018. So by the time we analyzed it, wrote it up, and it got published earlier in 2020, that's why the end date was in 2017. So this is going to be a little movie of annual rainfall across the basin starting in 1975. So the scale over there on the right shows in millimeters and inches. So it goes from about 30 inches to 42 inches per year. And you can see it changing over time from the 70s all the way up to 2013 to 17. So let me go back and watch that again here. So I was talking over it, but you can see in the 70s, we were pretty close to about 30 inches across the whole watershed. And it gets progressively wetter, you'll notice, as it becomes more blue as we move through time. So you can see the biggest change was really in that last period from from the early 2000s through 2017 was the biggest changes we saw. So what we saw from this is, when we look at this at a smaller scale, we're not looking at it at a national scale, we see that the changes in rainfall aren't spatially uniform across the Maumee watershed. And this is the magnitude of change since 1975 to 77. So you can see, and there's some areas of the basin that had moderate decreases in rainfall. So these red areas were a decrease of annual rainfall of about 4 inches per year. We have some areas of the basin that really experienced no change in rainfall or small increases. And then we have some areas that experience large increases. This is over almost a 14-inch increase in rainfall in the southwestern part of the basin. So what about rainfall intensity? So we split rainfall into 5 different categories, going from trace rainfall to very heavy rainfall. And again, I put the inches in parentheses on the very far right there. So trace rainfall was less than 1/10 of an inch, all the way up to very heavy rainfall that was greater than 3 inches. And this is the amount of rainfall in one day. So again, the graph on the left shows the change in rainfall since the 1970s. And we can see that there's a lot of variability, and on average, not a whole lot of change for the trace rainfall, light rainfall, moderate or very heavy rainfall. Some sites had increases, some sites had decreases, but on average, across all those rain gauges, they were about the same on average. But the one that really stands out is that heavy rainfall. And that's rainfall that's from 1 to 3 inches per day. And that has consistently increased across most of the sites in the basin. And on average, we've seen that's about equivalent to a 1/2 inch increase in heavy rainfall per 5-year period over the last 40 years. So that's very significant. When you think about, we're seeing, 80 millimeters more, so almost 3 inches more on average rainfall as heavy rainfall each year. So how does this look across the basin? So this graph is oriented by kind of geography, where the sites are listed 1 through 23, where the lower the numbers, that's the southern part of the watershed, and the higher the numbers, that's the northern part of the watershed. And I put some city references on there going north to south just for from some reference. So when we look at the northern part of the watershed up in Michigan around Hillsdale, you can see that there were heavy increases in heavy rainfall, kind of noted by that teal blue color, but a lot of those were offset by decreases in the other kinds of rainfall, so light and moderate rainfall. So that's why in those areas in the north, we were kind of seeing a small decrease in actually overall annual rainfall, even though heavy rainfall was increasing. But as you move south, you kind of see those bars shift more to the right side of zero, more positive. And that's because not only were we seeing increases in heavy rainfall, but also all the other rainfall fractions too. So therefore, we were getting these big increases in total rainfall during the year. We analyzed this data by season to see when these changes occurred. I have all the seasons but spring kind of grayed out here because spring is where most of the action has been. During the spring, we've seen the biggest increases in heavy rainfall and the biggest increases in total rainfall across all these sites. And that's important because spring is already the wettest season. This is a graph showing soil moisture deficit over, I think it's over a 10-year period from one of our edge of field sites. And you can see soil moisture deficit is lowest in those March, April, May, slightly into June timeframes on average. So the lower the number, meaning the soil's wetter. And it doesn't take much rainfall when the soil's this wet to trigger a discharge event. So therefore, if we already typically have wet soils in the spring, we're increasing our heavy rainfall during that at that same time. We see big increases in discharge, particularly during the spring period. Kind of moving on from the rainfall, well, how does this influence the flow in our rivers? So again, we had the 12 river monitoring locations from the USGS. So we separated those out into the sub watersheds that they would each contribute to. And we see that the patterns in tributary discharge follow the same spatial patterns as rainfall. Again, this graph shows the change since the 70s. And we can see kind of in the northern half of the watershed, we see no change to slight decreases in the amount of discharge. Whereas in the southern half of the basin where we had the most rainfall, we see increases in tributary discharge, with the biggest increases kind of just south of Fort Wayne, really in the St. Mary's. So also, what has this done to the magnitude of flows? We're seeing bigger spring flows. So that's flows that are greater than the 90th percentile at 7 of the 12 tributaries. And in contrast to that, we're seeing smaller summer flows. So those are the flows that are less than the 10th percentile at 4 of the 12 tributaries. So we're kind of seeing this big contrast of really wet springs, even drier summers. So it's an interesting management challenge for agriculture when we think about it that way in terms of trying to grow crops. So how does this relate to phosphorus load? These are long-term trends. So this is we use a statistical method to look at the long-term trend over these. Because we started this in '82 because of the gap in the Heidelberg data from, I think, 78 through 81. But this is the long-term trend in discharge at Waterville in millimeters per month versus the long-term trend in dissolved phosphorus load at Waterville. And you can see there in January of 1982, when we started this analysis, discharge was kind of right in the middle, about 27 millimeters per month. It decreased pretty consistently through the early 90s. Again, this is the long-term trend. And then since about 1991, discharge was going up, and so was the dissolved phosphorus loading. From this, it would be really easy to say that, rainfall is controlling our phosphorus load. It's not anything changing with management. It's not anything else. But we need to be really careful when we make those kind of conclusions, because there's a lot more that's changed other than rainfall over the past 40 years. Essentially, there's a lot of different trends that have been occurring over this period. There's been changes in water management, changes in nutrient management, changes in soil management. And untangling all those different trends is very difficult. And it's something that I haven't really been able to do yet. So to quickly wrap it up, rainfall amount, intensity, and seasonality have all changed across the Western Lake Erie Basin. The tributary discharge has followed a similar pattern to rainfall, and it's correlated to dissolved phosphorus. So the changes in rainfall have no doubt influenced our phosphorus loading, but we still have a lot more work to do to separate the effect of changing weather from other factors that may have also influenced phosphorus loss. And again, just as a reminder that I said at the beginning, this is just a high level summary of all the different analyses we did in the paper that we wrote. So if you'd like more details, please contact me and I can get you the paper. And again, here's my contact information. My email is listed there. If you're going to email me, make sure you get the 2 in my email address. I get a lot of emails from the original Mark Williams. And also I have my Twitter is listed there below. This is a personal Twitter account, not affiliated with USDA, but I do share paper updates and other things through that. And with that, that's all I had.
That's very good, Mark. I appreciate it. Really like the high level view. I would like to remind those that are tuned in that if you can use your chat, if you have questions, and I would like to just pose one to you before we move into Chris Winslow. And I started writing down some questions, Mark, as you were going through, but then you kept answering them as you went along, which I thought was great. But I do, right at the very end, you said detangling the rain events and the increased phosphorus loading, that we've got to be careful in making that assumption. But early on, you talked about our soils are wetter. And obviously, a sponge can only hold so much water. And when we get a rain event, it's going to discharge. Would you have any insight on, as we change management practices on the farm and we try to increase the soil health, which is going to retain some water, would that be a component of soils being wetter, and thereby we're going to end up discharging water quicker?
So part of this analysis that we did was we used the paper was very statistical in nature, in that we used a lot of different statistical techniques to look at these kind of these long time series to see if we could detect any change in patterns. And one of the things we did look at was we tried to get a handle on, has watershed storage changed? So that's not specific to soil health. I mean, that would also include changes in drainage, intensity, and all those things that influence storage of water on the landscape. But what we did see was that overall, in most of the sub watersheds that we looked at, we saw that watershed storage has increased over the past 40 years. So on average, most of those sub watersheds were storing more water than they were in the 70s. Could that be because of soil health? Is that because of difference in how we drain it? Narrower space drains. We can't say that what specifically is causing it, but there is more storage. But at the same time, the increase in intensity and rainfall kind of overwhelms any increases in storage that we see. So when you think about a rainfall event, you have a bunch of water all at once. So even if those heavy rainfall events are kind of still overwhelming the system, even though we have a general trend of increasing storage in the watershed.
All right, very good. Thank you, Mark. Appreciate that. That generated a couple of really good questions. We're going to go to Chris Winslow right now. We're going to hold some of these questions that just came in and see if we can squeeze them in. Chris Winslow is with the Ohio State University Stone Labs. He holds a session every year called State of the Science on the Western Lake Erie Basin. For fear of oversimplifying, Chris kind of addresses the trends that Mark has shared. Once the weather hits the ground, what's happening? And just like Mark talked about how it's an overview, and Mark could probably take an entire day to educate us and understand that, Chris could do the same. But as always, science is always evolving. And I'd like to just share this as a quick example to get us to start thinking about some of Chris's findings that he's going to share. And this is kind of an old revelation, but it's probably worth sharing. Some of you who are a little gray-haired might remember the big deal of acid rain, a decade or more ago. And predominantly, if I have this correct, remember I'm an urban guy, that it was sulfur from coal-burning power plants was one of the largest contributors. So the scrubbers were put on the smokestacks, really cleaned up that air, and acid rain began to get reduced. But then science began to determine that free sulfur that was coming across the cropland was aiding up and tying up the extra phosphorus and it's that extra phosphorus that has a tendency to create some algal bloom problems. So we took 2 steps forward in eliminating acid rain, but a step backwards in that we didn't have that free agent out there to tie up the excess nutrients that were out on the croplands. So Chris, I hope I didn't jumble things up too much. Chris Winslow with OSU, we're ready to learn.
Great, and I'll move through some of the early slides fairly quickly because I think many have seen it, but I do want to make sure we're all level set. Thanks, Dan, for that, and Mark, great talk. I loved how you said you were a deeper dig, and coming from an aquatic guy, I'm always a deeper dive, so that's awesome. I like that perspective. So as you can see from the title, basically, I'll talk to you about the history of Lake Erie algae, talk to you about some nutrient sources. Many of you have seen this, but just want to make sure, again, we level set. Talk about some of the tools, some of the recommendations that are coming out that we know from previous science. Talk to you about some research efforts that are ongoing right now at a very, very high level. But I also want to identify some gaps. And so Mark did a good job of saying this, is that there are a lot of questions that we still need to either dig or dive into. And so I want to highlight some of those. And then I want to spend a little bit of time at the end talking about legacy phosphorus, because this is one of those sources of nutrients that are driving the loading into the lakes. So let me see if I can get this to forward. So this is our history of blooms in the lake. So what you're seeing is basically the western and central basin of Lake Erie. This is basically a satellite images that have been converted into this heat map. So basically warm colors are high bloom densities, cool colors are lower densities, and the black is non-detect. You can see what jumps out at you is we've been dealing with these HABs since the early 2000s, and that it varies from year to year to year. Basically, what this is showing is that peak bloom biomass over a 30-day period. This is that same data basically on a graph form. So the severity index is running up the vertical axis. That's not a units. Again, this is relative to each year's bloom. You will see that we have seen an increasing trend since the early 2000s till now. The largest blooms on record were 11 and 15. If you remember those years, those were very wet previous falls to planting or the spring of planting. You will also note that there are years where we're below what this trend of increasing blooms in years. I will point out to you that 12 and 16 were pretty darn dry years. So what this does is tie nicely into what Mark was talking about, is that when we think about nutrients, usually we only talk about phosphorus, but when we think about phosphorus and nitrogen, it's just not how we interact with those nutrients on a day-to-day basis, but it's in this grander context of a changing climate around us. So this increased rainfall. So I thank Mark for his great talk here earlier. Nutrient sources today, again, since the mid-70s, we've been doing a lot to reduce wastewater treatment plant inputs. Dan alluded to this a little bit earlier in his talk. So if you look at all the point sources from wastewater treatment plants in the Maumee, these are specific to Maumee, it contributes about 9% of phosphorus coming out of that river during these spring events. The CSOs, which I'm glad Dan pointed out too, we in Ohio, by 2020, so during our COVID year, 40 of the 62 communities that have these have basically control plans in place. But even on one of our wet years, so I have 2013 listed here, even if you add up those CSO discharges in that specific year, it's less than 1% of the phosphorus making into the system. So we're not saying that CSO shouldn't be addressed for things like pathogens and viruses and the other stuff that are coming out of these combined sewer overflows, but it's not a driver in phosphorus, it's a contributor. As far as septic systems, we know in Ohio, and these are average numbers, there are, I hate using the word hotspot because it connotes negativity, but there are hotspots where more of these septic tanks are not performing properly. But basically, we're seeing that about 4% of the phosphorus is coming from some of these septic systems that either are not designed correctly, or not functioning correctly, or have some instances where they're discharging directly to our tributaries and ultimately our large lakes. There are, at least in Ohio, state regulations coming into play that are aiming to reduce these, so free and reduced loans to upgrade septic systems. Early on, we had a lot of suggestions that a lot of this phosphorus was coming from our golf courses and our suburban and urban areas. We know that since 2013, Scott's Miracle-Gro has removed phosphorus from its fertilizers. Not entirely. The starter fertilizers will have phosphorus because if you're growing a brand new grass, you need that pulse of phosphorus. But if you go into any Menards, Ace, Home Depot, Lowe's, and grab a maintenance fertilizer off the shelf from Scott's, it won't have any phosphorus in it. So we know we don't have current application, over application rates in our urban and suburban areas, but there may be some places we could address our attention here. And last but not least, we always talk about is the lake itself contributing nutrients to drive these blooms. So this is often referred to as internal loading. So the phosphorus in the bottom of the lake that during storm events is resurfaced. We did some studies. Sandra Kosick-Sills I saw was on the call. She was associated with some of these early studies during, I think it was 2014, 2015, looking at that resurgence of nutrients from the bottom of our lakes. And in Erie specifically, it's only 3 to 7% of the phosphorus. And so when you add all these up, basically it points to what probably everybody's been hearing is that most of this phosphorus is coming from our ag landscapes. And I do not say that in a negative context. This is not a blame game. A lot of those contributions that are coming from these ag fields are from things that we did in the past that we just know to do differently. I would argue that many of these ag contributions are not from a malicious intent. It's just we're learning as we go. I do put the word versus in here at that last bullet because some of our internal lakes, like Grand Lake St. Mary's is one of those, the internal loading contribution from shallower lakes, inland lakes, can be much higher than 3 to 7%, but these are numbers that I'm showing you for Lake Erie. Last thing I want to show, which again, Mark highlighted, is we need to work on the rivers themselves. For too long, we've been treating the nutrients coming into the system as the rivers are just a tube, a pipe that takes the water from the edge of the field and dumps it into Lake Erie. And we now know that rivers are playing a role in here, and we're working really hard to figure out what role they are playing. Are they adding nutrients? Are they drawing down nutrients? And that's a complex problem that we're learning right now. Just to show you a picture, this is 2011, again, the second worst bloom on record, just to show you how big and bad these blooms can get in Lake Erie. I want to point to Dan again about, the nature of science, right? It's an evolving piece, right? So we get some information, we retest those hypotheses, and sometimes our answers come out in a slightly different way. But I want to say that we cannot stop progress for perfect. So yes, the science is going to change. We're going to learn new things. We're going to recommend new tweaks, usually minor tweaks, but sometimes major tweaks to what the producers are doing on the landscape. But I will tell you that all the science is pointed to the fact that we're directionally correct. So we're not going to come back to you, I don't imagine, saying, oh, what we told you 5 years ago is wrong, let's switch gears. So I just want to let you know the nature of science is that we don't have absolute proof here, but we are directionally correct enough to start moving in the same direction. And some of those things are listed here. So all of you are familiar with, in Ohio, we're on the 4R nutrient certification program. For us, it was Senate Bill 150 back in 15 or 16. But again, this is right fertilizer source. So when you use manure versus commercial, right time. So how is the weather driving when you apply? Right rate is we're telling folks you got to have a nutrient management plan. Let's soil test before we apply. And right place is where I put here is where that nutrient is needed. And so we're talking about subsurface placement here. And so these are all things that we're recommending to producers anytime we have the chance to engage them. I will say that some of these are easy to say but hard to implement. For example, right place. To band or inject fertilizer is not a cheap undertaking. It requires new toolbars and heavier equipment in some instances to apply. As far as right time, yeah, it's easy to tell a farmer not to be out on frozen ground or when it's, forecast of rain. But if you look at a year like 2019, that's tough for a producer to be in that space because of heavy spring rainfall. Frozen application, again, we know that when you put fertilizer out on frozen ground, we can define frozen in many different ways, but when you do that and you have your spring thaws, we've shown that that's a decent contribution of nutrients. And again, this rain and forecasted. I put these out separately because SB1 is Senate Bill 1 in Ohio. So actually these are in law that we can't in certain areas apply on frozen ground or when rain is in the forecast. I don't want to glance just easily at that forecast because Mark pointed to this too. This saturated soil is a good component too, because there are instances where the soils may be dry enough, and Mark showed that in his early data, that if you put your fertilizer down and then there was a heavy rain, there is a high possibility that those soils are still going to be able to hold on to those nutrients because they have that water holding capacity and they are so dry. So coming up with blanket rules like this, we need to recognize that climate, circumstances, different farms will respond differently to these different rules. I already mentioned eliminate broadcast application. We got to adopt subsurface placement. Again, this is a tough one for producers, and we all need to recognize that we can't ask these farmers to turn the switch overnight because to get the equipment to put this in place is not easy. It's not cheap, but also putting subsurface placement of fertilizer also takes more time on the field. And if we're shortening the window that farmers can be out there because of spring restrictions and winter restrictions, again, this is not an easy lift. Soil testing is a necessity. Early on, this was difficult because soil testing could be expensive, and we didn't know how to best test our soils as far as where to take the soil cores. But I would argue now that a lot of the data I'm seeing shows that the cost for soil testing is often offset by a reduced fertilizer cost because you're purchasing more fertilizer. And in some instances, an increased yield because farmers are finding places that they thought had enough phosphorus and now are learning they need to apply more. Water management is key. I don't want to belabor this one because Mark just messaged this. You know, we're getting more rain and we're getting heavy flood events, more severe storms and more frequent storms. And then I don't ever want to end a talk saying this is all space and work that ag needs to be in. There are things we can do in our urban and suburban areas like lawn care recommendations of removing phosphorus from our fertilizer, reduce property runoff. So how can we keep water on our urban and suburban lawns longer? You know, so porous surfaces, rain barrels, water features. We got to work on those wastewater treatment plants. Again, 9% of the phosphorus is coming from there. And we need to resolve some of these poorly functioning septic tanks. But ultimately, the goal is we need to reduce the loads that came in 2008, which was a heavy wet water year, by 40%. And Mark and I are trying to hit on the way we do this. I always call it 3 buckets. We're going to get to this reduction by 3 different ways. One is by getting everybody on the 4R nutrient stewardship programs. And I think of this as our annual engagement or relationship with nutrients. So what are we doing on a day-to-day or a season-to-season use of fertilizer? And if we can do and follow the 4Rs, we can have a great reduction impact from phosphorus. We need to look at legacy phosphorus, and I'll get to that here in a couple slides. But then what Mark had in spades is water management. We got to figure out how to deal with it, changing climate. It's the reality that our producers are dealing with right now. And I'll preempt the question right now is the Lake Erie fix a quick fix? And I will say yes and no. I will say we know that if we get to 40% reduction relative to 2008, the problem goes away almost overnight, right? We've seen 2 years, I showed them in that earlier graph, where you have low rainfall, which by that nature got us to that 40% reduction, and the bloom was mild. The problem is the no part of this is that getting from where we are now to a 40% reduction is not going to be quick. We've got to get a lot of acres in different practices. We got to get a lot of subsurface placement, and I'll show you a figure to this regard later. So if we get to 40% reduction, problem goes away overnight. That's quick. It's the road to get from where we are now to a 40% reduction. A lot of ongoing research efforts. There are some folks on the call again that are tied to this, but basically in Ohio, it's the Harmful Algal Bloom Research Initiative. This is funded by the Ohio Department of Higher Education, has been funded since 2015. This is co-administered by Sea Grant, the program that I get to be affiliated with in the University of Toledo. To date, about $10 million in 70 projects have been put in place relevant to HABs. This is since fiscal year 15. Right now, we're actually currently looking at proposals for FY 20 and 21. We're about ready to give about $3.8 million, almost $4 million out in funding. And off the presentation here, I can give you access to these 70 projects that have been completed or are ongoing. But basically what we're trying to do is produce safe drinking water. We're trying to find out how these toxins affect human health. We're trying to look at how the blooms behave. When do they become toxic? Is it temperature that drives? What role does nitrogen play? What role does sediment play? So we're really looking at bloom behavior all the way down to the genetics. And the last one right now, we're looking at nutrient runoff. So how do we help those producers? And again, that's the key. Help the producers get to a space where they can lower their nutrient contributions to the system. Very collaborative. Can't tell you how much. Top left box is federal agencies, top right box is state agencies, the NGOs and the farmer groups in the middle, and the academic institutions on the bottom. Again, co-led by UT and Ohio State. The current call that's out, I just wanted to kind of let people know where we're looking right now from the agency and academic perspective. So those $4 million that we're giving out now, those proposals had to come in and address these things. So in Ohio, the DNR is looking to wetlands. How do we identify places to put them? How do we construct them? And how do we manage wetlands to reduce nutrients? In the ag, I'm going to show you a lot of sub-bullets here, but we're really looking at manure management practices and manure application practices. They want hard data coming from the academic institutions to show them best how to do this. We need the cost-benefit analysis of subsurface placement. As I've shown you, we need to be putting these nutrients under the surface of the soil, but not going back to tillage. That introduces potentially a whole nother issue with sediment loss. So how do we do subsurface placement, but how do we make it affordable for our producers? We're looking at adaptation to climate change. So really addressing some of the things that Mark brought up. How do we hold that water back without increase or impacting yield and causing increased phosphorus loss? How do we do drainage retention and detention? So if we're going to put drain water control structures at the ends of tile pipes and hold that water back, how does that water in the fields change the chemistry and potentially increase or decrease the release of phosphorus? We got to look at farmer perception or participation perceptions. We can't just come from the academics and tell farmers, you need to do X, you need to do Y, and you need to do Z. We need to bring those farmers into these discussions and figure out which things can they or can't they do from a fiscal or a behavior standpoint. From the Lake Erie Commission, again, I think Sandra Kosick-Sills is on here. We want to continue doing our modeling work, and I'll show you some figures and some slides here in a second that show the effectiveness of the H2O IO practices that are being deployed across the landscape. We want to do some paired and pilot watersheds where we take small, maybe Huck 12 watersheds, 5,000, 6,000 acres, outfit one with heavy BMP practices, leave the other one pretty much as a control, and see what is our bang for the buck and what is a reasonable ask of phosphorus reduction. We want some cost curves. Again, some of the behavior is easier to adopt when you can afford to do it. And so we're looking at cost curves to assess these top 10 H2O practices, which are again listed on the next slide. And then there's always that health background picture. What do we do to look at source water protection? So how do we make sure the water we're drinking is toxin free? These are the 10 practices that are the top 10 for the H2 Ohio investments for farmers. So please look at those, but all of these really resonate with the directionally correct information we have from the academics. There's a URL in here if you want this PowerPoint afterwards that has a video about this effort. And then this is a slide just talking about DNRs putting all of their eggs in the wetland basket, which makes a total amount of sense. And so they're doing a lot of work in that space. But I want to spend the end here talking a little bit about legacy. Here's what we learned from 2019. And so I'll break this slide down for you. Basically, think of the phosphorus is on the vertical axis in discharge, so the amount of river water coming out of the Maumee on the y-axis. And basically that line there is what we know is we can have some predictive power. So each dot represents a year from 2000 to 2018. And basically they sit nicely on this line. So what it says is that if you tell a scientist how much water or discharge is coming down the Maumee, they're going to be able to tell you how much phosphorus is coming with that. So if you look at this, we would expect 2019, the discharge was right around 5,000 or 5 kilometers squared of water. So you would expect it to be right on that line. In 2019, we saw it below that line. So it didn't fit the trend. The loads, total bioavailable phosphorus, were 24% lower than expected based on flow. And folks like Laura Johnson and Greg Labarge with OSU Extension looked further into that. And what they showed is the why behind this. And so this is some reasons why we might have saw less phosphorus than we would normally predict. And here it is. The image you're seeing is the normalized difference vegetation index. So it's showing how much plants were growing through satellites in 18 relative to 19. And you can just see there was less plants on the ground in 19 relative to 18. And if you look at the data, 41% of crops went unplanted in 2019 or of land, 5% in 2018 to give you a reference point. As far as commercial sale of fertilizers, 46% of the normal amount were sold during 2019. And the last one is that 15% of manure applications, of typical applications, happened from March to May. So there was not a lot of manure on the field. So what this tells you is that this indicates that not a lot of fields were planted, not a lot of commercial fertilizer was out there, not a lot of manure fertilizer was out there. And so even though you had high rain discharge, you didn't have a lot of runoff. So it talks to those 4 R's stewardship. If you're not putting excess fertilizer out there or you're putting down reduced fertilizer amounts, you can lower that phosphorus off the standard curve. Let me show you a little bit more though. Here's 2019 versus 2020. So in 2020, which is the figure I'm showing you here, the dissolved phosphorus hit right on the line. So if you would have told the modelers your discharge was X, the dissolved phosphorus was right on the line for Y. But if we look at 2020 total particulate phosphorus, so the phosphorus attached to sediment particles, it was off the line. And what that is showing us is that what happened in 2020 is a different story, where the farmers actually did a lot of tillage in 2020 relative to what they normally do. So folks that were doing no tillage or conservation tillage or whatever you want to call it, actually tilled because that year off from planting put a lot of hard soils, a lot of weeds in the soils. And so what it showed us is that when you go back out and till, you're going to lose a lot of sediment. The last thing I want to do is, again, talk a little bit more about this legacy. And this is estimating sources of contribution of our legacy phosphorus. Let me orient you here. So this is data from 2005 to 2015. The orange bar is the averages. And so basically it's point source. So these are like wastewater treatment plants, inorganic fertilizers. So this is commercial bought, manure application. And then if you sum those two together, it's the land application. And then so you've either got a point source contribution, a land applied application, or what's originally in the soils, and we will quote unquote this legacy. And so what I want to do is show you when you add up these totals, the first number is total phosphorus contribution. The parenthetic number is DRP, so the dissolved component. So if you look at the DRP, the major contributor for this is inorganic. So it's commercially bought. 45% of that phosphorus fraction is coming from inorganic. Legacy is the second player. Point source, basically wastewater treatment plants, is the third, and manure is the fourth. If you look at total particulate phosphorus, or I'm sorry, total phosphorus, legacy is the number one contributor, inorganic comes to second, and point source and manure round out the end. So what it shows you is that, yes, we can look at point source from inorganic fertilizers to commercial application as that 4R ready use today, but a big component of the contribution in every year is going to be that legacy component, that soil, already present soil phosphorus. And so this legacy matters because legacy phosphorus can serve as a chronic source of this pollution, right? So even if you stop all surface application, you're going to have this legacy already in the soil phosphorus contribution. Further, this masks some progress that we might be making on the field. So if we're not addressing legacy soil-bound phosphorus while we're doing our 4R nutrient certification, you may see in some years where it doesn't look like you're making progress for the efforts on the landscape because it's washed out by that, literally washed out by the legacy contribution. And so our management of phosphorus will vary depending on where your source is. So we need to think about when we're deploying cover crops and things like that, or buffer strips, is that addressing ready use 4R today application of nutrients, or is that addressing legacy, or both? And so that's why I'll pull up this last slide for everybody. These are some of the modeling efforts that are coming out of J. Martin, Margaret Kelsick's lab. And basically what we want under Annex 4 with that 40% reduction is we want 9 out of 10 years we don't see a bad bloom. And so this baseline is how many years basically we're seeing these bad blooms, right? Or bloom-free years in this case. So 3 out of 10 are bloom-free. We want to be up at the 9. And what you're seeing is that these are percentages that they plug into the model of cover crops, subsurface placement, buffer strips, and it shows you how do we move the needle from where we are now to where we need to be, which is this green line. And what you're seeing is that cover crops, subsurface placement, buffer strips, all of these things, even in percentage rates of 60, 50, 78% deployment, we're not getting all the way there. And what I would argue in some of these models is that if you start putting in retention basins at the end of, bioreactors at the end of drain tile pipes, or restoration of these maybe high legacy fields, those things might help in aiding in this chronic background legacy contribution. And so I'm going to pause there because I definitely working with Dan and Greg Lake, I wanted to make sure there was time for questions here. So I'll pause there, and Dan, I can actually stop sharing slides and open it up to you to facilitate some questions.
That's great, Chris. Thank you very much. And I think it's just very telling, the collaboration that you're involved with and the other scientists studying all the different facets here. You touched on 3 or 4 topics that are going to be upcoming by some of the other presenters without getting into a lot of detail. So I appreciate that. I think that's just an indicator, is that the scientists are aware of what each other's doing. They're making sure they're not overlapping, but they're connecting their findings and their research. We did have a couple questions come in, so I'm gonna share 1 or 2 here to see what we can get through, and I want everybody to know about 9:55. Then we'll just take a break. We'll take a 5-minute break, and then we'll pick right back up at 10 o'clock for the second session. So there's been a lot of activities. I wanted to focus on the wetlands. I know that the U.S. Army Corps is partnering with the city of Defiance on a very small demonstration site to test materials to see what might be the best materials to absorb extra nutrients, phosphorus maybe specifically. And it looks like there's a possibility they may be building a larger one. And I don't want to get a club out here to beat anybody, but you know, here we are on the Indiana side, contributing probably 20% of the water to the Western Lake Erie Basin. And even though we're a much smaller piece in our state, we're looking at regulations to eliminate the wetlands, and that just really seems counterintuitive. So my question, Chris, is what is the talking points that we might be able to share to, one, preserve our wetlands, or two, encourage the exploration of, can we find some of these retention areas to begin to keep more of it at the source where the rain falls? What suggestions would you have?
Yeah, in the wetland space, I'm glad you asked. So under Governor DeWine's H2 Ohio initiative, the Department of Natural Resources is leading kind of that wetland charge. What's going on right now is there's a team of academics across 6 different institutions developing what we're calling a wetland monitoring plan. What we're trying to do in Ohio is to make sure when a wetland is deployed is we need to be taking the same types of measurements so that we can be comparing different wetlands to each other. Just like an ag field, a field is in a field is in a field, a wetland is in a wetland is in a wetland. And so under Governor DeWine's initiative, I would argue that the 40-ish wetlands that are going to be constructed over the next handful of years, 2 years probably, fall into 4 categories. Coastal wetlands, so those that basically rim Lake Erie. Treatment train wetlands, where the water basically is pulled from either an ag ditch or a river. It's run through a wetland, goes through a series of pools, and then exit backs out. So there's a discrete entrance and an exit. They're looking at flooded floodplain wetlands, so rivers that often flood, and seeing what we can do as far as wetland construction along those rivers. And then the other one is what you're kind of talking, these retention and detention bases, where we're finding normal depressions within the landscape within potentially a producer's field and converting that to a wetland. And so what's going on right now is we're monitoring all of these as they're being deployed, because what we imagine is that all of these wetlands are not going to function the same way. And so right now, unfortunately, I feel like all the data that exists, or most of the data that exists on wetlands, it's going to one wetland and seeing, does it draw down nutrients or not, but not really assessing what attributes or features or what times of years these different wetlands function the best. So Dan, I will tell you that I think a wetland is a great tool in the toolbox for these depressed areas in some fields. And I think it is going to be a good strategy if we identify legacy fields, if we can get those legacy fields to move their runoff through these wetlands. But right now, I don't think we're at a place where we can tell you which type from a cost benefit analysis is going to be best. But I do think it is one of those amazing tools that is probably going to have to help us out in the presence of these legacy fields. And again, I hate that term, but kind of the horse just left the barn on this, is that when we see a farmer, there is not going to be one farmer's entire field that is a legacy field. The problem with legacy is we're probably going to find these little chunks of land, these 10 acres here, 40 acres here, 30 acres here. These are going to be tough to track down and identify solutions for.
Chris, that's very helpful. And I appreciate you defining that all wetlands aren't the same and they can have different functions. And towards the end of your answer there, you sort of headed into the second question that came, and we may finish up with this one because we're short on time. But your comparison of where the loading is coming from, comparing to maybe municipalities and then commercial fertilizer, manure, and then legacy. Pretty startling facts, at least in my eyes, and I think some of the other ones on where these sources are. But the question was, legacy seems to be a reasonably new understanding and a huge driver. I like the phrase you used, that it's beginning to cover up some of the successes that maybe we're having in other areas. Can you expand any more on what sort of research is being done to better understand legacy and where you may see that headed in the next 3, 4, 5 years?
Yeah, and I can specifically render a researcher named Jay Martin and his team. They've got funding to work with certified crop advisors, and basically working with those certified crop advisors to identify farmers that they work with that likely have legacy, or that have legacy fields, right? Those crop advisors go out there and tell these producers, you need to apply phosphorus here, you are high here. But those certified crop advisors are the trusted resource for these producers. So that's been the connection between the academics to the farmers with legacy fields. And what Jay is doing right now, and I don't know, but off the top of my head, let's say 14 different legacy fields. He has now established positive synergistic relationships with those producers. And he's actually deploying some of those practices that we think can trap some of that legacy phosphorus. And so we have just like Kevin King and his paired watersheds in Ohio, and I know there's others that are in other states. Basically what we're trying to do is get some pilot paired fields here. Let's put this practice on this legacy field and see how quickly we can draw down that phosphorus. So I think there will be some information coming out here on which practices will help those farmers address that. And that's what we're hearing from the producers. It's not, once they know they're a legacy field, they're not opposed to doing something to get that nutrient reduction in place. They just don't know which tools and how much it's going to cost them to get there. So I think that that's valuable resource going on, or research going on right now.
That's really good to hear, Chris, that we're using the certified crop advisors to take the science right to the producers. Farmers are busy enough trying to figure out how to run that business, and I like maybe the invite that you had, that if we identify that we've got some legacy nutrients in an area, go to the professionals and say, what are some of the tools I could use to address this?
And if anonymity has to follow that, that's not a problem, right? The academics don't care whether it's Jane or Bill or Frank's property. They want the data to show we put this on this property and this was the result. And so most of those, actually, I think all of those farmers aren't going to be revealed from where they're located and where their fields are in their history. So it's just making that trusted connection, because ultimately the solutions we have here are going to revolve around the relationships we have too. And so I think that's a critically important step.
Absolutely. Thank you, Chris. I appreciate you sharing that. Mark and Chris, thank you very much for taking some time this first hour. That was a ton of science dumped on us. We'll take a 5-minute break, and then we're going to come back and we're going to start talking about the economic impacts, both urban and rural, of addressing some of these water quality challenges, and some of the things that were just suggested in these first presentations. It does cost dollars and cents to implement those, and so we're going to hear what some of those challenges are to implement it. So everybody that's with us, thank you very much. We're just going to take a couple-minute break, and we'll fire right back up at 10 o'clock. Thank you.
Sandra, I see you're still on. Thanks for your comment about the arrow. I can either shift that direction or remove it entirely. You don't need that to show the trend. So thank you for that comment.
Yeah, I just think it's a little misleading is all.
100%. You know, and on my last comment, it's relationships. You don't want to be in this negative space all the time. So removing that arrow makes it's a simple change. So thank you for making that suggestion. I'll pull it for future presentations.